So we'll start with that green key that I have just handed you, and it's in that separate multiple choice packet. Okay, so we did problem number 1 yesterday, and we did that in class. As a reminder, remember the difference between how to know if you are using a t-score or a z-score or a z-test. And it's totally, completely based off of, not if they told you it's a normal model population, but what? What is your decision? Standard deviation. So if you have just sample standard deviation, which is S of x, you're going to use your t-scores. If you have population standard deviation, which is sigma, then you use z. Okay? So that's kind of conceptually what's happening with that. All right, so number 2 is about the qualities of the t-distributions. They are wider and more varied than the normal model. Okay, and so as your sample size gets bigger or your degrees of freedom gets bigger, you will get closer to the normal model, but at first they are wider and more varied. Okay, number 2, actually, or 3, is a problem not about t distributions or z distributions or whatever. It's about the generic or the sampling distributions. So that was back kind of a throwback problem to chapter 18 when we had that computer app where I showed you the population, and then we would drop down an average, and then it would give us our sampling distribution, okay? And so this question isn't asking, you know, when do you use the t distribution or a sampling distribution or even. It says, how do you know this thing right here, this sampling distribution is normal? And we have a song for that. And it was that if n is large enough, it doesn't matter. The shape of the population, so see, the population could be any shape. The sampling distribution will be normal. And that was because it was the central limit theorem is about the shape of this sampling distribution and the population. Okay, so that's why it's answer C. So that was kind of a throwback problem. You might have been tempted to put answer choice D because that's kind of something we're hitting about or talking about in this test, but there's some throwback things on here. 4 I'm not going over. It's a pure put it in your calculator, get your answer problem. Okay. Moving forward. All right, 5 is a review problem about the changes and how to affect your power. So do you recall this little thing that I made for you to remember how to increase your power? So to increase power, your alpha and your n can go up. Alpha and n can go up, or your beta can go down. So I look for the ones with the biggest alpha and the biggest n, and that's answer choice C. All right, let's see. Number 6 was also a plug it in your calculator and get a p-value. So you recognize by reading that it's a one sample t-test, and you go put that stuff in there and get C. Okay, 7 is also just a plug into a formula and seeing if you can plug the correct things into your formula. This was a proportion formula. Proportions always use z's. All right, so the answer is D, but I put distractor problem answer B, or distracting answer B in there. That's a common mistake students will do. I haven't really seen it much this year, but this, let me tell you what happens. The students say, oh, they recognize this is two-tailed. So I remember when I do two-tailed problems by hand, I got to double the p-value. Okay, and that's great. Yes, you do have to double the p-value. Doubling the p-value does not mean doubling the z-score. And I want to give you a visual of that. Look here. The p-value is the probability of getting this sample or something more extreme if the null is true. So this area is the p-value. That's what you multiply by 2. Do not multiply the z-score by 2. Multiplying the z-score just means you're saying your sample is not located here, but located way out here at 2z. And that's wrong. So it's not the z-score that you multiply by 2. Okay. And then finally, on this page, I threw in an old problem that is just based off of population and not even a sample at all. It was just asking about a single car. So the standard deviation you use is just 5. If it had been a sample, then you would do the sample, the s of x divided by the square root of n, but that's not the sample standard deviation. So you got a z-score for 30, a z-score for 40, and you found the norm CDF'd from your negative 1.2 to positive 1.8 to get that area there. Okay, been kind of moving quickly through those. Questions on those so far? Okay, good. Let's see here. Okay, so this is about comparing the math versus the verbal, seeing if there's a difference in those for per person, basically. How many of you guys have taken your SAT and got a big difference in your verbal versus math? Mine is like a 270 point difference between my verbal and my math, so pretty big difference there. So this is paired data, because then you would take each person's data for both of those items, okay, and find the difference in them. Okay. Yes. Oh, okay. Yeah. So in fact, so this is called a chi-squared, and I know we want to call it chi because of, isn't that's what you call the in the hair product things, chi? Yeah. Okay. Yeah. But this is actually a chi. This is the Greek, and it's chi. And we're going to learn those starting next week. And chi-squared problems are not for one proportion or two proportions, but multiple proportions. So like to test an entire bag of 6 colors of M&Ms. That's what we'll do chi-squareds with starting next week, okay? All right. Moving on to number 10. So this one I had to kind of think about because my gut reaction, my initial reaction was to pick B, but the population standard deviation from each group is unknown. That would answer the question, why would you be doing a t-test? That's not answering the question that it asks. It asks, which of the following are necessary assumptions? That's our random, independent, and large enough stuff. Okay. So let's think about that, random, independent, and large enough. So what size are these samples? 10. So these are too small of samples. So that means, oh, we got to deal with that. They're not large enough. So what's our first line of defense if they are not large enough? Yeah, go check the reading up there and see if the population is approximately normal or normal stated. Then you don't have to make a histogram or a dot plot. Okay, so that's what you want to do there, and that's why D is the answer. The populations would have to be normally distributed because the sample sizes are too small. Okay, all right. Now, for number 11, let's talk about how to increase the size of a confidence interval. What part of the interval makes it get bigger or smaller? Wider or narrower? The margin of error, the length of those whiskers, and that's the margin of error. So that's what makes it get wider. So I want to refresh your memory on the formulas. Okay, so for proportions, we've got p hat plus or minus your z star, and then your standard deviation for proportions. For means, you have sample mean plus or minus your t star and your standard deviation for means. So I've identified the margin of error is the part where? Where's the margin of error located in the formula? Okay, after the plus minus. So here is our margin of error. So in order to make that the biggest, I need the critical value to be bigger and the standard deviation to be bigger. So let's now address how you make each one of those things bigger. So what do you do to make critical value bigger? It has to do with what in general? How spread, like the middle spread, what is that? Confidence, yes. This is determined by how confident you are to be. I have a visual here. See this? 80% confidence would put your critical values here. 90% confidence is more spread out critical values, and 99% is even more spread out. So in summary, the more confident you are, the more spread out it is, and you have a bigger critical value. Okay, so that means, first and foremost, more confidence. Okay? Next, let's address how to affect this standard deviation. How do I make standard deviation bigger? What component affects it? Yeah, this is going to affect it. You want to go smaller sample size because that makes it more varied. Smaller sample size makes it bigger. So, in summary then, I can say down here, I need the one with the biggest confidence and the smallest n. That's what I'm looking for, which is B. Okay, so that's how you work through that. All right, questions on that page? Okay. All right, number 12 is straight up definition. Not going over that one. Number 13, so we need to have a little discussion about this term significant. Something is considered significant if you reject HO. So your data is statistically significant if it's far enough away from the null hypothesis that it causes you to reject it. Okay. Now let's address p-value. The things that make you reject it is if your p-value is what? Less than your alpha. So that's what we're looking for. So significant is based off of you having a p-value lower than alpha. Something is considered significant if its p-value is less than alpha. So that brings us to this number 13. It says, is this significant at the 5% level or at the 1% level? So we need to address that. I need a p-value. But they just told me the t-score. They're telling me my sample is out there at 2.615. So how do I get that p-value? It's the probability of getting that sample or something more extreme. So I need this area right here. That's more extreme. TCDF 2.615 to 99 degrees of freedom 14 will give you this upper p-value. Okay, it's like our norm CDF we used to use, but we're TCDFing it. And we get a p-value of 0.0102. So there's our p-value, 0.0102. So in order to be significant, you have to be smaller than alpha. So which alpha is that p-value smaller than? Is this smaller than a 5% alpha? Yes. So this is considered statistically significant at an alpha of 5%. Is this number smaller? Is this p-value smaller than 1% alpha? No. It is not smaller than 1%. So it's not significant at the 1% level. So it is at the 5%, but not at the 1%. Okay? Questions there? All right. And here is another problem based off of a formula, straight up. So I'll just leave it at that. You'll have formula chart. Yep, formula chart. Okay, so that was all of that. So we've now gone over just that first multiple choice, right? Okay. Okay, so let's do the second multiple choice. That one was wordier, but you're going to start seeing some themes. So pull out the white answer key that you were given, and turn in your packet to page 44. So white answer key and your packet, page 44. Okay, so here we go. don't know what just happened there. Okay. Well, there you go. Okay, so here we go. This first one. Oh, by the way, I've kind of, overall, I think some keys to this whole packet here is being able to read the problem and figuring out what kind of problem it is. One mean, one proportion, two means, paired, okay, that kind of stuff. Remembering how to do inverse T for critical values. And also something else that that's concept of being significant. Significant at a perfect level. So we're going to see that kind of repeated several times in here. All right, here we go. Number one, so add this information. So you kind of have to think of it in terms of formula. I guess, so we're thinking of it in terms of formula. What ends up being the key is knowing that this is over the square root of n, so we're putting in 16 there. Okay, so checking that we're putting in 16 there, and then getting the correct critical value. So finding the correct critical value, that T star. And so the key is it's based off of, let's review how to get that. It's based off of 95% confidence. So we have 0.025 in one tail. So a critical value T star is inverse T of one tail, comma, degrees of freedom, which was 2.13. Okay, so do not forget that. That is your key to getting a critical value. And so that is how we get 2.13. Before we go any further, I will tell you, let me just kind of make a little side spiel, because this is an important thing to, we'll see it several times in the review. Oh my gosh, when I was grading your quizzes, I mean, besides like being sleep deprived, nothing is more irritating than seeing this same mistake over and over again. So here I'm going to use the whole, what in the standard deviation are you thinking if you tell me a p-value is 2.32? Because a p-value of 2.32 means there's a 232% chance of getting that sample or something more extreme if the null is true. You cannot have a p-value above 1. So please, please, if you see a p-value that comes up as a whole number and it's above 1, which is what that would be, look at the end of the line. Times 10 to the negative 20th. That is like 0. Grr. Gosh, I can't tell you. 15 to 20% of people put that their p-value on that non-dominant dominant switch hitter problem was 2.32 over and over, and it just made me mad. Now, if you put that, I followed your logic, which said that you failed to reject because it's greater than alpha, and I gave you all credit for that, but boy, was I tempted to just be so mad at that mistake that I was going to just mark it all wrong. I'm telling you. So, please, please, if you get a big p-value, look at the end of the line. Okay, back to this. That's my little soapbox. There you go. Okay, number two. If you walk through all of those things to read carefully, it's discussing qualities of T distributions, and remember that they are more varied. T distributions are more varied. As the sample size or the degrees of freedom increases, then your T distribution will get closer to the standard normal curve. All right, as your sample size or your degrees of freedom increase, you will get closer to the standard normal curve. They are more varied. Okay. And then this problem here, so let me talk you through the logic of this one, because man, this one is I mean, look at all this reading. I did try to buffer your multiple choices and make them a not so much reading as this, and a selection of some problems that are just plugging in the formula, some problems just straight up can you do inverse T stuff and get the formula right, sprinkled in with some theory items. Okay, so it's kind of a good variety of types of questions. So after reading this question, I went to my answer choices and I realized that, these answer choices are talking about being significant at the 1% or the 5% or the 10% level. So my brain is thinking, oh, this is referencing being significant. So, I probably need to determine what the p-value is. All right? That's the key. So if it's asking about significance or being significant at a particular level, you need to get the p-value. So therefore, I came over here to the data that was given to me, and I put that in as a 2-sample t-test for means to get the p-value. And guess what the p-value was? Was it 1.46? Heck no. It was not 1.46. It was 1.46 times 10 to the negative 4, so it's 0.000146. That's lower than in alpha at 0.01. Therefore, it is significant at the 1% level, giving you answer choice A. Okay? So identifying what your answer choices were different as helps you kind of understand what they're going for there. All right. Moving on. So, number 4, I recognized that this data was given to me in before and after terms, so I was like, straight up, I need to go do an interval. So I did in my calculator, I did a t interval for paired data, and that's how I found the answer. So I straight up did that one in the calculator and then found the answer choice that worked for it. You're welcome to go through all the formula stuff, but I didn't. Number 5 is another one. So again, this is reading the problem and figuring out what the heck kind of problem is this. 1 mean, 2 means what? That's why we were practicing. It's all mixed in together. So we want to know the p-value. Based on the information they give me, old and new, I can tell it is a 2-sample t-test. When I run a 2-sample t-test, voila, I get a p-value of 1.628 times 10 to the negative 6th. So that's how I got the p-value, which I guess I didn't put what it is. Oh yeah, duh, that is 0.00000 whatever, 16828, so it's below 0.01. Okay. All right. Number 6. Okay, look at how straightforward number 6 was. That is a basic knowledge question. Can you find a critical value? T star. Can you find a T star? And so that is straight up, put it into your calculator of inverse T of 1 tail, comma, degrees of freedom. Boom. All right, number 7 I was asked about by quite a few people. Okay, so let's take a look at this one. So the issue, people recognized, oh, it's about margin of error and I need to solve for n. And so that was great. But what happened was people were like, whoa, I got a T star. How can I get a T star if I don't know n? Because I got to get degrees of freedom. Well, the key is it was not a mean problem. It was about percentages. And percentage or proportion problems are always z-scores. Therefore, the formula didn't involve t-stars, it involved z-stars. So it was inverse norm of 1 tail and no degrees of freedom. Okay? Furthermore, it didn't give you did not give you the proportion. It didn't give you the population proportion. So, because true p is the best it can be. But if you don't have that, see if they give you p hat. Well, they didn't even do that. Okay, so we're going to use the best, we're going to go with what we can do. We won't, please don't cry, just use 0.5. So that's what I did there. And then the rest is algebra 1 to get your answer. Okay, number 8 is a total just put in my calculator for a t interval. Total just did that. So not going over that. All right. Number 9. Okay, this was pure. Can you look at what they give you and identify what this problem is about? So this kind of is what we did yesterday, reading a problem, identifying what this is about. It was a test for 1 mean, and it was 1-tailed because it asked for less than or greater than. And number 10 is a straight up definition that we talked about of t-scores and z-scores when you use them. And so it was A. Okay. Are you seeing recurring concepts over and over again? Yes. I think finally I've given you enough of these theoretical multiple choice ones for you to kind of see what's going on and for you to practice figuring out what these are about. Now, I got quite a few questions on this problem as well. The interesting thing is that for this problem, you didn't even have to do any math on it. So let's discuss how you do this problem without any math. Okay, so we're reading through here. It says, which of the following gives the p-value? So I know that a p-value is going to be based off getting a critical or a t-score or a z-score and go greater or less than, whichever. Okay, so there's how I'm going to get my p-value. So look at my answer choices. Some of my answer choices have t's and some of my answer choices have z's. So the first thing I'm going to do is figure out, is this problem going to use t's or is this problem going to use z's? So let me read. Da 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 da. Here's what it's giving me. La 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 la. Da 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 da. Oh, here's a sample of 16 with the mean of 4.3 and a standard deviation. Oh, So that must mean that my standard deviation I have is a sample standard deviation. Okay, voila. Sample standard deviation. Therefore, T's or Z's? What? T's, okay? So, A and B are out. Yeah, was that really a T? I don't know. Okay, good save. All right. Next, I see my answer choices have a greater than or less than. Okay, I could also do this degrees of freedom thing. The sample size is 16, so what's the degrees of freedom? 15. Okay, so it's not that. All right, so here I am. Now I'm down to answer choice C or D, one of which is a greater than and one of which is a less than. Okay, well, people, if you've got yourself a t-score of 2, that's a weird 2. Okay, if you got yourself a t-score of 2, which direction is going to give you a p-value? Greater than or less than? Greater than. Because a p-value is the probability of getting that sample, or more extreme. More extreme is going up. So therefore, it's t greater than 2. All right, so you see some just conceptual understanding walking through there. There was no math involved in computing. Okay. Was that all on that page or did I skip? Oh, yeah, okay. So here we go. All right. Which of the statements is true? Okay, so these go around being significant. Okay, talking about like so statement 1, there is sufficient evidence to reject the null hypothesis at the 10% level. So that, in order to reject it at the 10% level, your p-value is less than alpha of 0.10. If your p-value is less than 0.10, is it going to be less than 0.5? Not necessarily. Is it going to be less than 1%? 0.01? Not necessarily. If you're in the top 10%, you're not necessarily in the top 5% or the top 1%. So 1 is out. Number 2, statement 2, whether you use one or two-sided tests is typically decided after you gather data? Heck no. It's based off of what you're wondering about the claim. Okay, 3, if a hypothesis test is conducted at the 1% level, there's a 1% chance of rejecting the null. And that's not necessarily true. That is only true if the null hypothesis is true. Because if you think about it this way, here I want to draw you a picture. If the null is true, then here's your top 1%. Okay? Well, what happens if the null is not true? What happens if your data is based like that? Then is the probability of rejecting the null, is this 1% up here? No. So that upper 1% is only the case if the null hypothesis is true. If it's not true, then it's whatever. Okay. Moving on, I think this one was a straight up put in your calculator, so you realized that it is a one proportion z test, and you put it straight up in your calculator. You could do it by hand, but anyway, there you go. There's your answer, G or D. Okay, that was the end of the multiple choice questions. Any questions there? Okay, so now we're going to go to page 56 in your packet. In your personal packet, go to page 56. And that is in the pink key. Problem, it goes, but it actually, I think, on some of the white keys that you have, I accidentally copied this in there. So some of your white key, do you need one of those white keys? Oh, you got it. Oh, okay. All right, so in your packet, the work that you did, it's page 56 on, but you can look at it, it's probably in the pink key, number 14. Go to number 14 in the pink key. So again, I'm not going over the free responses that I had you do. There was just a few of those. You can look at those in the pink key, but also just go off of what you were missing on your quizzes. Okay? All right, so we're going to start at 15. I had you not do 14. 15, I'm not going to do too much. It's just, I mean, it's pretty foundational logic, understanding of what a hypothesis test is. You start off saying the two populations are equal, and then you see if they are something else, greater than, less than, or not equal. Okay, here's a review of type 1 and type 2 errors, so let's remember our definitions. So type 1 error, if the null is really true, and you get a sample that causes you to reject the null, that's a type 1 error. So type 1 error is when the null is really true, but you get a sample that causes you to reject it. The meme that goes along with that is the Ryan Gosling picture where he says, "Hey girl, I shouldn't have rejected you." Okay, because the null is really true, so I shouldn't have rejected you, but I did. Okay? All right. Here, let's remember our type 2 error. Type 2 error. Oh, type 2 error. You failed to reject a false null hypothesis. Type 2 error, type 2 error. So you fail to reject, so you don't reject a false null hypothesis. Failed to reject a false null hypothesis. And the meme on that is that weird squinchy face, and he says, "Why you no reject the null? Why you no reject the null? Because you were supposed to, because it's a false null hypothesis." Okay? All right. Now, I don't have it on here, but power is related to these, and can't remember who the guy in the meme was. I can't recall his name. But he was some famous guy. He's some hot guy out right now, you know, whatever. I don't remember his name. No, he was somebody else. But he said this. He said, "I see you raised your sample size. More power to you." See you raised your sample size. More power to you. Yes, that's who it was. Yes, Mark Wahlberg. Okay, yeah. Mark Wahlberg. Okay, so, hey, I see you raised your sample size. More power to you. You know, we got to get the chin jerk in there, okay? More power to you. All right. Okay, so here, remember your p-value definition, because, you know, I wouldn't put it past there being multiple choice answers that run through this, and you got to know it. P-value is the probability of getting this sample or something more extreme if the null is true. All right, so I'm got you singing those songs. Here we go. Number 18. If you were to run a test, what do you think you would expect to happen? Well, the point to the matter is 86 is not in the interval. Since 86 is not in that interval, I'm probably going to reject the null hypothesis of 86. Okay? Looks as though I would say I have evidence that it it's less than, whatever it is less than 86. Okay? All right. And this number 19 is just a straight up, can you compute a T-star? So that's a basic computation. If you miss that problem on the test, then I'm just going to say sorry, because I tried to give you a bone of just a basic computation problem for you to get one right. And so, all right, but let's take a look at number 20, A in particular. All right. So this problem says that we got null hypothesis of mean is 14 and tested against mean is not equal to 14 at the 2% level. What does this mean, 2% level? It's tested at the 2% level. What does that mean? That's your significance level. That's the size of the rejection region. So the size of your rejection region is 0.02. All right. So now I know I've got 2% area that is my rejection region. How do I know where that rejection region is placed in the curve? How do I know if it's in one place or another place or somewhere else? What will tell me? What do I look at to know where that 2% is located? Perfect. The alternative hypothesis. So by looking here at the alternative hypothesis, I can tell my 2% rejection region is split amongst two tails. So I've got 1% down here, 1% up here. That makes it 98% in the middle. Therefore, that's my confidence. Okay? Now, suppose the alternative had been one tail. Mu is less than 14. That would have put the entire 2% in the lower tail, making the mirror image up here, giving a different confidence in the middle, 96%. That's why that alternative is so important. All right. B is straightforward. 14 is in there, so it's possible. 21 is, do you know that an X bar goes smack dab in the middle of that interval? Hope so. You can find it that way. And look at 22. It's another one of those significance problems. So 22 says, you are statistically significant at the 10% level. So you are rejecting at the 10% level. Your p-value is less than 10%. Are you going to be significant at the 5% level? Not necessarily. If you are less than 10%, are you less than 5%? Not necessarily. But are you less than 20%? Yes. Okay, and here we go. Final tricky one. Well, not tricky one, but one I just need to make sure you got down, that you understand what's going on here. So, for number 23, they tell you once again the significance size of 10%. So the size of the rejection region is 10%. Now I need to identify where it is located. And what do I look at to see where it's located? HA. So part A says it's one tail, upper tail. So the entire 10% is up here in this upper tail. So to get this T star, I'm going to inverse T of what's below it. And what's below it is 90%. So I'm inverse T'ing 0.90 with 14 degrees of freedom. I guess it told me somewhere samples of size 15. Yeah, sample of 15 eggs. Okay. But B says it's a two-tailed problem. Therefore, the entire 10% is split between the two tails. So I don't have 10% in a tail. I just have 5% in each tail. So that's different location. That makes the critical value being inverse T of 0.05 with 14 degrees of freedom. And there are two of them, the positive and negative version of the 1.76. Okay, and finally, we got the lower tail. That puts the entire 10% down here, so you know you've got that lower T star that mirrors part A, so negative 1.35. Okay, questions on those? All right. The last two problems, 24 and 25, are asking you to understand what an interval about a difference is telling you. Okay? So this is about the difference of two items. So what does the null hypothesis always tell you if it's a problem about a difference? The null hypothesis is that there is a difference or that there is no difference. What does the null hypothesis always say? That the no difference, the groups are equal. Okay, so keep that in mind. See, oh, well, I have it written right here. The null hypothesis is for difference problems is always that there's no difference. So if I look at this interval 3 to 6, I want to see if a 0 is in it, because a 0 being in it would imply no difference. Well, here, the entire interval is above 0. So what does that seem to imply? That there is a difference, so I'm going to reject that null hypothesis. Okay, but look at the last one. I've got an interval going from -7 to +2, so the important thing to see is that 0 is in the interval, so there could be 0 difference. So there could be no difference. Okay. All right. Any other final questions? That's all I can do for you. Yes, ma'am. Okay. Words of what kind of, like 1 proportion, 2 proportion?